Hello and welcome to this lecture on RF pulses for the course UCSF Biomedical Imaging 201 Principles of MRI. This is from MRI the Basics, Chapter 3. First, the interesting MRI picture of the day, and maybe at least very colorful. This simulation here is illustrating actually an RF coil. That we're going to talk more about the purpose of RF coils in this lecture. But these silver gray rungs around the outside are what's called a birdcage RF coil. And then in the center, this is a simulation depicting the expected magnetic flux density within a human head with the tissue properties of a human head. And showing the variation in the magnetic field that can be created by such a birdcage RF coil. So hopefully some of that will make more sense as you go through some of the material in this lecture. So I'm going to start here with a disclaimer that this textbook, MRI the Basics, uses a sort of partially quantum mechanical explanation of RF pulses, but in fact you really need no quantum mechanics to understand MRI, which is fortunate for me because I do not know a lot of quantum mechanics, and I greatly prefer the classical mechanics explanation, and that's what I'm going to demonstrate in this lecture. So this is a case where you can use this material in this lecture notes as really a reference, and then the quantum mechanics aspects introduced in the textbook are not needed. However, I will also introduce the Bloch equation, which is a differential equation that governs almost all MRI behavior. And we're not going to do directly solving the Bloch equation, but we will be using the results of the solutions to the Bloch equation throughout this course. So I'll introduce at least the mathematical formulation there, and there's a bunch of more description about it in the MRI Education Resources Git repository. Okay, so here are the goals for this lecture. Why do we need to perform RF excitation? What frequencies are used in an RF pulse? What is the RF pulse flip angle? What is the lab versus rotating frame of reference? What RF pulse calibrations are important? And why is the RF power important? Okay, so I'm going to start with this review in this picture of RF signal reception. So recall what our signal comes from is the precessing or rotating net magnetization, indicated by the white vector M here. And as this basically little magnet rotates around, it creates an oscillating magnetic field around it. Now, when a oscillating magnetic field is occurring within a loop of wire or RF coil, or you can think of this also as an antenna, it's going to generate an electric current that is very easy to detect and process and actually ultimately use to create our image. Okay, so we want to get into this state and recall the z direction here is the direction of the main magnetic field that the net magnetization is rotating around. And so we want to get our net magnetization into this state where it's precessing. But at equilibrium, the net magnetization is aligned with the main magnetic field B0. They're polarized, but the net magnetization will not be precessing. So it'll just be static. It's actually at equilibrium. It's static. It's giving us no signal. So how do we get the net magnetization, which we're calling this animation here is this large green arrow. And the solution to do this is to apply RF pulses. And in this animation, these are indicated by this red-orange band around. And what you can see is that it's moving this large or turquoise, I guess, arrow away from the direction of B0, away from the direction of the main magnetic field. And then we're going to be in the situation now you see it's rotating in direction. It's going to create this oscillation in the magnetic field that can then be detected in our antenna and our RF coil. But at equilibrium here, we're not going to get any signal. So what we need to do is we actually need to send in a little bit of this RF pulse, this RF energy. Okay, so showing that same picture again, how do we get this RF energy into the system? Well, we're actually going to have an antenna, our RF transmit coil, and we're going to send in some energy at the resonance frequency, or Larmor frequency of our spins, and illustrated like with my fun little animation here, is going to create that effect. Now it's very complicated to look at it in this picture where we're seeing the individual spins in the net magnetization, and what the classical mechanics explanation of MR says we can do is we can just look at the net magnetization. But before I get into that, I almost forgot, do want to introduce this concept of the RF pulse flip angle. So this is how the angle away from what we say is the z-axis, the main direction of the B0 field. So the angle at which the net magnetization creates from B0 direction is called our RF pulse flip angle. I'll illustrate that again in this picture, where now we've simplified. We can use what physics tells us and just look at the net magnetization to completely understand what is going on with MRI. So again, we're going to apply a amount of radio frequency energy into our subject. It's going to cause the net magnetization to deflect away from its alignment and equilibrium. It's going to be deflected by some RF pulse flip angle, in this case theta. Okay, so let's go more into detail about the RF magnetic field, or the B1 field. Remember, this is an electromagnetic wave or electromagnetic field. Maxwell tells us we have both electric and magnetic fields together. And it's actually applied in a direction that's perpendicular to the main field B0. So in this case, B0 is along the z-axis, which is the direction of our net magnetization, the white vector. And in our RF magnetic field, B1 is pointed orthogonal to that, in this case along the y direction, but we're going to actually move it around in the xy plane is what we're going to do for our representing our radio frequency excitation. And remember, and we apply these as short durations, 1 to 10 milliseconds, which is the reason we're going to call them RF pulses. So we turn them on for some short period of time to cause this flip angle effect. Then we're going to turn them off. And then when we receive our signal, and then we end up repeating. And so what's going to be shown in this equation is actually how this simulation is actually how the rotation occurs. And what you'll see here is the magnetic field is actually rotating at the Larmor or the resonance frequency. And this has a net effect of also tipping the net magnetization, or M, away from the z-axis. And we have to do this actually near the Larmor resonance frequency. And why is that? Why do you need this so-called resonance excitation? This is sort of fundamental to magnetic resonance, that can generate the resonance phenomena. We need to match the energy that we're putting in, the frequency of the energy you're putting in, to the frequency that the characteristic frequency, this Larmor resonance frequency of our spins. So a simple example is maybe the best I could find was this kind of silly cartoon here. Is going on a swing where you see you want to push or pump your legs in the resonance frequency of the swing itself, and that'll actually have you go higher and higher on the swing. If you do it incorrectly, like this, you push not with the resonant frequency, you'll actually go lower on the swing. And we want to be in the resonance condition, allows us to do large flip angles, to do significant perturbations of our net magnetization. And this MR compass example, which I'll go through in class, is also very useful to illustrate resonance excitation. Okay, so again, here's what this looks like in our depiction of our magnetic field, or net magnetization, excuse me, M, and then our magnetic field, which here we're representing with the yellow vector. And the behavior that's governing what they're doing in this simulation is actually the Bloch equation, which I'll show in a little bit. So this is, we typically will observe this behavior in what's called a lab frame, where everything is rotating at the resonance frequency. But to simplify both our math and also intuition, we'll often use something called the rotating frame. And if you can imagine, this is where we're actually just, you can think of it as we're moving our observation around at the same rate that these two fields are rotating around. So the same rate that the net magnetization is rotating around, the same rate that the RF induced magnetic field is rotating around. So, okay, our initial picture here, and then if we do this sort of rotating frame trick, where again we're just moving our observation point around, what's fundamentally happening is not changed, but we get this sort of nice it's clear what's going on, is that the net magnetization here you can see is rotating around the direction of our magnetic field created by the RF pulse. And typically, as much as possible, I'm going to use the rotating frame both for visualization and interpretation of what's going on in MRI. And here's another just example of that, shown in an only slightly different way. Another thing we can illustrate here is that we can do different amounts of flip angles. So the previous examples I showed were just 90 degrees. We could do a case like this where you see deflected the net magnetization 45 degrees away from the Z. We can also deflect the net magnetization like I showed in the other examples, 90 degrees away from the Z-axis, or as the case may be in my sloppy simulation, probably about 85 degrees. I hope you get the idea. And we can also, another common flip angle we will use in MRI is actually doing 180 degrees of flip angle. So going from the net magnetization being oriented with the main magnetic field to be oriented in the opposite direction of the main magnetic field. And what we can do with these various RF pulses will become more and more powerful as we introduce the concepts of relaxation. So what happens after, in addition to precession, what else happens after the RF pulse is turned off? Okay, so I've mentioned the Bloch equation a couple times. Here it is. This is our almost first principles equation of MRI. It governs the behavior of the net magnetization M in a magnetic field B. The magnetic field includes both B0, our main field, and includes B1 now, our RF pulse field. And it really describes the majority of the MR physics phenomena. It covers relaxation that I just mentioned, and we'll go through more in the next chapter. In our optional textbook, Nishimura Principles of MRI gives a very detailed and thorough treatment of the Bloch equation. And put up here some definitions, and we'll go through some more of this in class. But again, we have the net magnetization, we have some MR tissue properties associated with that, and then we have our B vector, which includes our main magnetic field. There's some changes on top of that field, including our magnetic field gradients, the RF magnetic field here as well. So I want to do here a brief example to illustrate, well, what if we just neglect the relaxation components of the Bloch equation, and what this Bloch equation says, this cross product says that the net magnetization M rotates around the magnetic field B with a left-handed rotation, and the rate of rotation depends on the amplitude of the magnetic field. So say we could have a case like this where our magnetic field is our static field only, so oriented along the z-axis, and our net magnetization might also be oriented along the z-axis. Actually, under this scenario, nothing, the Bloch equation says nothing happens. M cannot rotate around B because they are pointed in the same direction. Whereas if we are able to tip M away from the z-axis, we have still our magnetic field be pointed along the z-axis, then we'll get some rotation of the net magnetization around the z-axis here. Okay, we're going to be dealing more and more with this this type of visualization of the magnetic field and net magnetization vectors. Just an introduction to this in this lecture. A couple more important parts of the RF pulses is we actually need to do some calibration, or what's often called Prescan, to set up our RF system. We need to make sure we're at the right frequency. Again, this is so we have actually resonance excitation, so we can actually deflect the net magnetization away from the z-axis and get signal. We're going to need to adjust our RF power. How much radio frequency energy do we need to put in to generate a certain amount of magnetic field, which turns out that's going to dictate what our flip angles are going to be. And then the RF receiver gain. Remember, we're also using these RF coils to receive the signal. So after excitation and the net magnetization is processing, we're going to get that signal back in the RF coils, and when you adjust these gains depending on how strong the signal is in the given imaging situation. And to mention briefly there, RF power. I want to talk just briefly about that. So I'm going to draw here what would be a simple RF pulse, and often use the notation. This is E1 magnetic field over time, and it has some amplitude here, and it goes along for some period of time here. The amplitude here will be units of Tesla, or say maybe micro Tesla, time in milliseconds. But the other thing that's important about an RF pulse is the power. And the power is proportional to the integrated squared area of an RF pulse. And the reason this is important is for safety reasons. This determines how much actually we can be heating up the tissue with these RF energy, and so that's limited for safety reasons. And the concept or the limiting factor is called the specific absorption rate, and it's proportional to this pulse power. So something we need to know about our RF pulses. Okay, so that was a quick introduction to RF pulses, talking about why we need to perform RF excitation, what frequencies we've got in our RF pulses, what is the concept of an RF pulse flip angle, what is the lab versus rotating frame of reference, and when we're visualizing the effects of the RF pulse, what RF pulse calibrations do we need, and finally, why is the concept of RF power important? Okay, thank you for listening.